So this is my attempt to go ahead and explain the little quiz we took on Thursday. So we're going to draw the dot diagrams. I'm going to try and be efficient but not go so fast that I lose you along the way. The first thing you need to do when you're drawing a dot diagram, and this one is hard to read, for some reason it's kind of out of focus here, but it says PCl3. So the dot diagram we're looking at is PCl3. It turns out that the P and the Cl have their own numbers of valence electrons, and you have to figure out what those electrons are. So we said that everything in this column on the periodic table, the first column, has one valence electron. All those have 2 electrons all the way up and down this column. Then 3, 4, 5, 6, 7, and 8. So since we're looking at, in this compound, P and Cl, the P is right here, the Cl is here. So the P has 5 and the Cl has 7. So then when you add up the valence electrons for that molecule, you will have 5 and 7, but there are 3 atoms of chlorine here, so we have to multiply by 3. All right, so we end up with PCl3, where we have a total then of 21 valence electrons, because 26 valence electrons, because 7 times 3 is 21, P is 5, so you end up with 26. Next thing you do when you're drawing a dot diagram is draw a skeleton structure. And usually you put the least electronegative element in the center. Other things to consider that we mentioned were the things in the center. So if we say center, the least electronegative in the center, the one with the most open spots, goes in the center, usually. And the one that is closest to the middle of the table. So in this particular problem, P is the least electronegative because electronegativity increases as you go to the right. The open spots rule, the most open spots, P has 3 open spots because there are 5 in its outer shell. So it could get to 8, so the difference between 5 and 8 is 3. Chlorine only has 1 open spot. So by the open spot rule, P goes into the middle. And the one that's closest to the middle of the table, I think P wins in that regard as well, because P is further to the left and toward the center than chlorine is. All right, so those are the rules that you think about when you're drawing a diagram. So now we put the P in the middle, like that, and then we put the Cl on it, like this. Cl, Cl, Cl. So we now have the second rule we need to follow, which is draw a skeleton structure. We did that. Then we subtract 2 electrons per bond. So subtract 2 electrons for each bond. There are 3 bonds, so take away 2 per bond. You're going to take away 6. So take away 6. That gives you 20 dots to put in. So we put in our 20 dots so that everything has 8. Now this may be confusing because I just put in 1, 2, 3, 4, 5, 6, but these 2 electrons make 8. So the chlorine does have 8, even though I just put in 6 loose dots. And the same thing will be true for this chlorine and for this chlorine. So when I put those dots in, every atom has 8 except for the phosphorus. So if you double check, I've put in 2, 4, 6, 8, 10, 12, 14, 16, 18 of the 20, so the other 2 can go right there. Now everything has 8 electrons around it. The P has 8, the Cl has 8, and we're all happy. So now you're ready to talk about the electron domain geometry and so on. So what you do first when you're trying to figure out the geometry, now we'll skip over the formal charge for a minute. So you count the domains around the center atom. So count the electron pairs around the center. So in this picture, we have 1, 2, 3, 4 domains. Remember, and when you're counting domains, the multiple bond counts as 1 domain, and an electron pair counts as 1 domain. So in this case, we have 4 domains, which means when there's 4 domains, the electron pair geometry is tetrahedral. So this would be tetrahedral. molecular geometry around the center atom, since in the domains we have 3 shared and 1 unshared. You see that there's 1, 2, 3 shared and 1 unshared. That's a shared pair. That's a shared pair. That's a shared pair. That one's unshared. So when there are 3 shared and 1 unshared, we call that a pyramid. So it's pyramidal or pyramidal. The bond angle will be somewhere around 107 based on this sheet. Now the formal charge, we'll go back and look at that instruction. So formal charge, you have the valence electrons minus 1/2 of the shared electrons minus all of the unshared. And it tells us here to adjust the skeleton if necessary to minimize the formal charge. And you can't expand an octet for second series valence shell, which means that you would never see more than 8 electrons for any of the elements in the second series. But the third series, you sometimes do expand the octet. We will not worry about adjusting the structure to minimize the formal charge, but we do want to know how to identify it. So use this formula: valence electrons, half the shared, all the unshared. So for phosphorus, you have 2, 4, 6 shared, so half of that would be 3. So we had 5 valence electrons, I'll write it over here, 5 valence electrons minus half the shared, which would be 3, minus all of the unshared. There are 2 of them, 1, 2. So that gives us a 0 formal charge. Now dipole moment, is it polar or not? Well, here's where you got to think about the shapes that I had you draw. Since this is a pyramid, it's really going to look like this in 3 dimensions. And the electrons are going to be pulled toward the more electronegative element. So the electrons are going to go in that direction, back toward the back, down to the bottom here. And so the bottom of this pyramid is going to be a negative because the electrons are going to move in that direction. So the bottom is negative. That means the top of the pyramid is going to be positive. So the positive and negative are in different places. So that's what I mean by this. If the center of positive and negative are in different places, then the molecule is polar. Or you can think about charge vectors. So the electrons are going to go this way, they're going to go this way, they're going to go that way. Those vectors would not cancel each other, because if they were like people pulling on ropes, and they're pulling on ropes are all attached to that atom, and you pull this way and that way and that way, that atom's going to go down. And so that means this molecule will be polar. If you were pulling on these charges, the charge vectors, and the molecule didn't move, it would be nonpolar. For example, if you were pulling in this direction and in that direction, the molecule would not move, and that would be nonpolar. All right, so that's all for the first one. Now the second one, the BRCN, we add the valence electrons. So you go look at your periodic table. Bromine sitting right here. It's got 7. And C is in right here. It's got 4. And what's the other? N is right here. It's 5. So you got 7 and 4 and 5. All right, so that makes 16 valence electrons. So then you set up your skeleton structure, and we do this, and we do this, and we can see that we're going to run, we got 16 electrons, we're going to take away 4 of them, that gives us 12. I think you can see that if you put 6 here and 6 here, that's 12. And that would make the nitrogen full, and also the bromine full, but I would still need 4 more around the carbon. So then you have to decide, am I going to add a triple bond or 2 double bonds, because you're 4 short. So you add your valence electrons, you draw your skeleton structure. You notice I put C in the middle because C, remember the rules, C had the most open spots. C was closest to the middle of the table, and it was also the least electronegative among these. All right, and once again, these are guidelines. Sometimes 2 out of 3 apply. They don't always all 3 have to apply. All right, so now I'm going to put in 2 double bonds, and then I'm going to show you something about formal charge. All right, so if we put 2 double bonds in, because we were 4 short, we needed 2 more here and 2 more there, so you have 2 few electrons, put in multiple bonds. 2 short, we've said it was a double bond. If you're 4 short, you have 2 doubles or a triple. In this case, we were 4 short because I needed 2 here and 2 there. All right, now what we're going to have to do, I'm going to have to pause just for a second. It's Mike.
Hello, this is Mid-America Service calling for Michael Health. If this is Michael Health, please press 1. Otherwise, we are attempting to confirm your appointment on Monday the 20th. The anticipated time frame of your appointment is between 12 noon and 5 p.m. To confirm your availability, please press 1. If you will be unable, thank you for confirming your appointment. Please feel free to call us with any questions.
Okay, I'm back. Sorry, there was I have an appointment I had to confirm. All right, so we were 4 electrons short. So 2 and 2 right here. So just to make sure I made that clear, you have Br and C and N. We did that. We had 16 electrons. We take away 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I needed 2 more here and 2 more there, so I'm 4 electrons short. I put in 2 doubles. So when I do that, that gives me 8 electrons in the picture already. So now I have 8 more loose dots to put in. So you have 16, take away 8, gives you 8 dots. And now the octet rule is satisfied for everything. 2, 4, 5, 6, 2, 4, 6, 8, 2, 4, 6, 8. And then around the carbon, 2, 4, 6, 8. These are not there. All right, so that's one way to draw the picture. Actually, it turns out that a better way to draw the picture is with a triple bond, I believe. So let's try that. And you may not be able to tell the difference, but here's why. The formal charges for carbon is 0 in either case. So it's going to be 0 because you're going to have 4 minus half the shared. And in both of these pictures, there are 8 shared electrons. 2, 4, 6, 8, so half of that's 4. There are no unshared, so the answer is going to be 0. But around the perimeter, one of these pictures is better than the other one because in this picture you have 7 valence electrons for bromine. You're going to take away 1, there are 4 shared, so that would be 2 you'd subtract. Then all the unshared, 1, 2, 3, 4 minus 4. That gives you a formal charge of 1. And on this side, nitrogen is 5 valence electrons minus 1, 2. Half, there's 4 shared, half that's 2. Minus all the unshared. So 5 minus 2 minus 4 is negative 1. In this picture, you have 5 minus 6 shared, so half of that's 3, minus 2 is 0. And on this picture, you have 7 electrons minus 1 electron, because there's only 2 shared, so minus 1 of those, minus 2, 4, 6. So minus 1, minus 6, so you end up with 0. So here you have 0 for all 3 atoms. That makes that a better picture. On this little quiz, I would have taken either one. Okay, the electron domain geometry, since there's 2 pairs either way, is linear. And again, the way you find that, you look right here, 2 pairs, linear. Since there's linear is always linear for the molecular geometry, that also is linear. The bond angle in a straight line is 180 degrees. Now, in terms of polarity, if these atoms are the same on the outside, then the molecule is going to be nonpolar. But this atom is not the same as bromine. As a matter of fact, nitrogen is a little more electronegative than bromine. And that's a little bit hard to tell. You might have to look it up. But if you know that they're not the same atom on each side, it's going to be a little bit polar, at least a little bit polar. And that is the answer to that question. So really, technically, these are yes, they're dipoles. Polar means dipole. All right, so now we're ready for CH3Cl. Let me say one other thing about these 3 elements on the periodic table are the most electronegative elements, hands down, on the table, those 3. So if you see one of them, that's going to be the more electronegative of these 3, for example. N was the most electronegative. All right, now CH3Br. So we got 4 valence electrons. I'm going to start assuming you know how to count these now. 1 times 3 is 3. We have 7. 7 and 7 is 14 valence electrons. 4 and 3 is 7, and then 7. So we set up our skeleton structure. We put the C in the middle because it's got the most bonding spots. We put the Br on one side, and we put H on the other side. Now remember, H only wants 2 electrons. So in this picture right now, we've got 8 of our electrons. We have 6 left to put in. We can put those 6 dots right there, and that satisfies everything because hydrogen only wants 2, and carbon has 2, 4, 6, 8. So now we're looking at how many domains around the center. Looks to me like it would be 1, 2, 3, 4. 4 domains, tetrahedral. 4 shared, no unshared. So that's also called tetrahedral for the molecular geometry. So that's tetrahedral, that's tetrahedral. The bond angle for tetrahedral is 109.5. By going into 3 dimensions, you get more than the 90-degree angle that you see in this picture. So if we drew it in 2 dimensions, it'd just be 90. But in real life, you can go into 3 dimensions and you get a bigger angle. It goes into this kind of geometry. So this is just showing you real quick. So those angles are bigger than 90 degrees. You can see them from this angle. See, that's a bigger angle. If it was 2-dimensional, it would look like this, and that would be 90. So I'm hoping you can see that by going into 3 dimensions. Whoops, I didn't get in the camera. So it looked like this would be 90. So I'm hoping you can see that by going into 3 dimensions, the bonds can get farther apart. And that's desirable because electrons are negative and they all repel each other. Alright, so the center atom formal charge on this guy would be, you have 4 valence electrons, you take away 1 of each of the shared, so that's 4. 4 minus 4 is 0. There aren't any unshared around the carbon, so we're looking at 0. And this molecule is also going to be polar. The reason for that is that, pardon my cord there, is because this guy is not the same guy as that, so the electron is going to shift a little bit toward the bromine, and that creates a polar molecule. So that's, yes, it's a dipole. All right, next one, CbR2O. You got 4 valence electrons. 7 times 2 is 14. You got 6, so you've got 18 and 6 is 24 valence electrons. Then you draw your skeleton structure. The C goes in the middle. You have an O out here. You have a Br. You have a Br. Okay, you're going to take away 2, 4, 6 electrons. That gives you 18. You can see that we're going to have a problem because if I put 6 here and 6 here, then that gives us 12, and 6 there makes 18, and I would be out of electrons, but I would still need 2 more for the carbon. So what you have to do instead is put a double bond in here, because you're going to be 2 electrons short. Remember, we're 2 electrons short, add a double bond. So I put the double bond in. Now we subtract 8. 24 minus 8 is 16. And we put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And now the dot diagram rule, the octet rules, is satisfied for everything. There's 2, 4, 6, 8. 2, 4, 6, 8. Okay, now what is the domain, electron domain geometry? So you look at the chart. How many domains? Remember, a multiple bond counts as 1 domain. So you got 3 domains. 1, 2, 3. So 3 domains, trigonal planar. And since all those domains are shared, see, that's shared, that's shared, that's shared, that's 3 shared, no unshared. So the molecular geometry is also called trigonal planar. The bond angle, since it's a triangle in a plane, 120 degrees. The formal charge on the center atom, you've got 4 valence electrons. I'll write them over here. 4 valence electrons. Take away, there's 1, 2, 3, 4 shared pairs. So half of that is 4. 4 minus 4 gives you 0 because there aren't, minus 0 gives you 0 because there aren't any unshared pairs around the carbon. So they're all shared. 4 shared pairs, half of that is 4. So your formal charge is 0. Is it polar? Well, are these the same element all the way around? No, you got an O out here. So that means the molecule is polar, it'll have a dipole moment. Okay, now SO3 negative 2. Add your valence electrons. So sulfur's right here, 6 and 6 for both of those. So you'd have 6 for the sulfur, 6 for the oxygen, but the oxygen would be multiplied by 3. So you're going to have a total of 24, and then this little negative 2 means that there are 2 more beyond that. So our total number of valence electrons is going to be 26. So we have 26 to work with. So we put in S, put our O's in around here. Now we have 6 in our picture. So we take away 6, that gives us 20 valence electrons. So minus 6 equals 20. Okay, so 20 valence electrons, we put them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Then we have 2 more that can go there, 19, 20. So everything is happy. The octet rule is satisfied. If you look this up on the internet, you may find it with double bonds, because if you add a double bond, you can minimize the formal charge, but we're not going to worry about that. So we would say that is the picture. Our domain geometry, we've got 4 domains. 1, 2, 3, and 4, because a double bond, or unshared pair, counts as one domain. So 4 domains, tetrahedral. Looks to me like there are 3 shared and 1 unshared. So tetrahedral with 3 shared and 1 unshared, we've already said, is pyramidal. So this would be tetrahedral, this would be pyramid. The bond angles would be about 107, somewhere around that, based on this thing, 4 domains, 107 when there's 3 shared and 1 unshared. The reason they're different is because this unshared pair spreads a little bit more and pushes them down closer to each other, pushes these bonds closer. Okay, the central atom formal charge, and this is not going to be wonderful on this one. So you have 6 valence electrons for sulfur. You have 2, 4, 6 that are shared. So take away half of that is minus 3. Then you have 2 unshared. So 6 minus 3 is 3, minus 2 is 1. So our formal charge on the center atom in that picture is 1. Okay, is it polar? Well, yes, because it's a pyramid. If it's a pyramid, it has this kind of shape again. And so the electrons are going to shift toward the more electronegative element, which is oxygen. So it's going to be negative on the bottom, positive on the top, and it is going to be polar. Next one, C2H2Cl2. So you've got 4 times 2 is 8, plus 2 is 10, plus 14. So you have 24 valence electrons. On this one, the C's have to go in the middle, and they'll be connected to each other. The reason they have to go in the middle is because they've got the most bonding spots, and they're closest to the center of the periodic table. So we put our H's and Cl's on and keep it kind of symmetrical, but there's more than one way to do these. I'll draw it like this. All right, so then we have of our, how many electrons? 24. We have 2, 4, 6, 8, 10 in the picture, so we have 14 to put in. I'm going to put in 6 here. I'm off task here. So 24, we've got our picture drawn like this. You could put the Cl here or here or here. It doesn't really make any difference where you put them, but you need to attach them to the carbons. The carbons need to be in the center. So electrons that are in the picture, 2, 4, 6, 8, 10. So you got 14 to put in. If you put 6 here and 6 here, that's 12 of them. You'll need 2 more for each carbon, so that's 2 more here makes 14. So you're going to end up being 2 electrons short. So if you're too short, what you have to do is add a double bond. Remember we talked about that. If you don't have enough electrons to go around, too short, add 1 double bond. So we add the double bond. Now we subtract 24 minus 2, 4, 6, 8, 10, 12. That gives us 12 to put in. So 1, 2, 3, 4, 5, 6. We don't need any around either carbon now. And that's our picture. Okay, the domain geometry on the center left, that's this one right here, will be trigonal planar because there's 3 domains. So 1, 2, 3 domains. There aren't any unshared pairs, so that is also trigonal planar. Once again, I'm looking here. 3 shared, no unshared. So it's trigonal planar for the molecular geometry. Bond angle, the angles here, 120 degrees. Center atom formal charge, or center left, we did center left here, so 4 minus, there are 4 shared pairs, half of that's 4. There aren't any unshared, so the formal charge is 0, so that's a nice picture. And now the last question, the way I drew this, it's going to be polar, because the electrons are going to move toward the chlorine like that, and they won't cancel. However, if I had put the chlorine over here and the H up here, it would have been nonpolar because they would have canceled. So this picture I graded on the way you drew the way you draw this determines your answer to that. All right, now ClF5 is the last one. So Cl has 7. Fluorine also has 7, but that's times 5. again, the way you know that, they're in this column here, 7. So Cl, and then you put 1, 2, 3, 4, 5, like that. I'm cheating a little bit because I know kind of how it's going to shape up, I think. All right, so that's 7 times 5 is 35, plus 7 is 42. So you got 42 valence electrons. 2, 4, 6, 8, 10. Take away 10. Gives you 32 to put in your picture. Okay, so 32 electrons. And if we put them in, we'd put 1, 2, 3, 4, 5, 6, and that makes 8 around there. Okay, there's 30 of my 32, so the extra ones have to go on the center. So now you're looking at 1, 2, 3, 4, 5, 6 domains. 6 domains is octahedral. And of those domains, 5 are shared and 1 are unshared. 1 is unshared, so that's a square pyramid. So you have 1, 2, 3, 4, 5 shared, 1 unshared. So that is octahedral because there's 6 domains. It's a square pyramid because one of the domains is unshared. All right, if you want to see just three-dimensionally, see, you can kind of see it right here. That's your square pyramid. Not a great artist, but you get the idea. All right, so it's a pyramid. Okay, bond angles on those are 90, it says on a little sheet. Formal atom central charge, you had 7 valence electrons. You take away 1 for each of the shared pairs, half the shared. So 7 minus 1, 2, 3, 4, 5, minus 2 for all the unshared gives you 0 formal charge. And this looks asymmetrical, doesn't it? The electrons are going to be, these are all in a plane, these 4 in a plane. This is up above the plane, so the electrons are going to be skewed a little bit toward the top, and that makes this polar. All right, so we'll stop the video here and save that one, and I'll do the other side, the other test.